Today, you are going to discover everything you will need to know about piling with Wagners Fibre Reinforced Polymer piles, including pile requirements, design methodologies and driving techniques, comparing composite piles to steel, timber and concrete, and how Wagners FRP piles stack up to other composite piles. Good morning and welcome to our webinar on piling with Wagners FRP. I'm Kelly Stewart, Marketing Manager at Wagners CFT, and I'm here with today's guest speakers, Wagners CFT Technical Lead, Dr. Ali Mohammed, and Chief Technical Officer, Michael Kemp. Ali is a structural engineer specialising in civil composites with a strong technical background in FRP products at the material level, individual components, and full-scale structures. Ali oversees all technical elements of Wagners CFT projects globally and is passionate about FRP as the material of the present and future. Meanwhile, Michael is an ambitious CEO and business unit leader with more than 20 years' experience at Wagners, where he has spearheaded significant growth and innovation. Currently, he oversees Australian operations for Wagners Earth-Friendly Concrete and is focused on expanding EFC into international markets. Michael is also responsible for the global growth of Wagners Composite Fibre Technologies and the technical development of new products. With a Bachelor of Civil Engineering from the University of Adelaide, Michael combines his tertiary qualifications with deep expertise in business processes, strategic development and product innovation. We're also joined by Wagners CFT General Manager for Australia New Zealand, Ryan Leeson, who will be facilitating today's Q&A session a little later on, and Wagners CFT Marketing Officer, Georgia Lance, who will be telling us a bit more about where to find piling installation instructions and details in our technical document library a bit later on. So welcome Ali, Michael, Ryan and Georgia. Before we get started, just a few webinar protocols. We are recording today's event and will make the recording public via the Wagners CFT YouTube channel. You can ask a question anytime during the webinar via the chat bubble at the top of the screen. However, we will hold your questions over to the end of the webinar for the Q&A session. And for anyone having difficulty accessing the chat facility, feel free to text your questions directly to my mobile phone, and I've just put my mobile number in that chat for you now. So let's dive into today's webinar. Michael, over to you.
Thanks very much, Kelly, and good morning, everyone online. I'll share my screen and we'll get underway. So today we're going to talk about the application of our fiberglass profiles to piling. At Wagners, we've been pultruding fiberglass profiles for over 20 years, and we've used those profiles for various different applications. We've used them in crossarms, we've used them in boardwalks and bridges. At the end of the day, we're making continuous cross-section profiles like steel or aluminium, but out of fiberglass. And we've adopted those profiles to different applications. Piling has been one that we've been working on for actually 15 years in April this month, from their first real commercial installation of piles. And today we'll walk through a number of those projects. We'll start off with where it all started. So 15 years ago in April, up in Mackay, our first commercial piling project. We'll talk about composite piles and why you would use them as opposed to steel or timber or other traditional materials. I'll hand over to Dr. Ali Mohammed, and he'll give us an overview of the fibre layup of composites and design considerations with composite piles. So we've been trying to get as much into that design element as we can. We'll talk about pile driving methods. We've seen numerous different methods employed. And then we'll talk about the future and where we see composite piles heading. So the first composite pile project that we undertook was actually up in Mackay. And I thought I'd start our webinar today just by talking through the project. We'll sort of highlight how we've used them, and then we'll go into a few details. Up in Mackay, the council was looking to put in a walking trail system, or they have put in a large walking trail system called the Blue Water Trail. So it's much bigger than just this area. It extends all around Mackay. This section here is behind the Canelands Shopping Centre, for any of those that know Mackay, on the banks of the Pioneer River. It was an area that was sort of out of the view of the public, and unfortunately it suffered the impact of off-road vehicles. So people, I guess, on their own time, taking motorbikes and so on out and tearing up the environment there. They were looking to put in a designated walking track area to, I guess, minimise the disturbance and to provide greater accessibility to the public. On the diagram there, you can see the intended path of the trail. Where the trail was above a certain RL, where the flood level of the Pioneer River got to, so if it's above that level, it was a slab-on-ground pathway. If it was under that level, an elevated boardwalk was required. On the initial site inspection, we found an old bridge on the left-hand side, so completely rusted out. So we knew that we were going into an area where traditional materials were going to struggle, and that a composite boardwalk would be first choice, certainly for council, due to the lower maintenance requirement long term. Additionally, acid sulfate soils were present, so they didn't want to be sort of digging up or disturbing the ground. Much preferred option was to drive through it. So just to give you a picture of the project, so it's a very simple boardwalk. We use our fiberglass pultruded profiles as, in this case, piles, bearers, joists, and we had a decking put on top of that. The benefits of composites in this type of environment, there's the corrosion benefit, but they're also very light. So we were carrying 6 metre lengths with 2 men, easily carrying 6 metre lengths into site. And when you've got quite a long, narrow site, so we've got a fairly narrow area that we were allowed to have machinery and so on. So all the gear is being sort of carried along the length of the boardwalk. Light materials we find greatly help installation costs. So we're designing for predominantly pedestrian loads and very small vehicle loads. Not highly loaded by today's standards, but certainly, a 5 kPa design load or a 3 kPa design load for these boardwalks is common. And then potentially, golf buggy type loads or small maintenance vehicle type loads are often allowed for. Upon driving the piles, on this case, we used a drop hammer approach, and the pile sections, the 125 square sections, were driven in by dropping the hammer. As our first commercial project, we'd done some trials, obviously, before the project, but across the course of this project, with over 410 piles driven, we used it to really, I guess, get used to piling and test a few different things. So we're looking at the height of the hammer as we were dropping it to the pile. And across the course of the project, we did dynamic testing. So you see on the left here, we're doing PDA testing. We set up concrete blocks and a structural support frame, and we were able to do static testing. And of course, we were correlating that to the Hiley formula. So we can determine, based on the mass of the hammer and the height it drops, effectively using the energy equation, you can reverse calculate the vertical capacity of that pile. So comparing the sort of the field technique, the Hiley formula, with the static test and the dynamic testing across the course of the project. We did record all that, and we've produced a paper which we're making available to everyone on the call today in a follow-up email that'll be sent out. But you can see on this table that we've been able to get very good correlation between our Hiley formula, I guess, based on the driven set of the pile, the calculated capacity, and then the static and dynamic testing. So that, I guess, this initial project, and over the course of those those 410 piles, we were able to achieve a very good confidence level in our ability to base the foundation of our boardwalk and bridge structures on driven composite piles. Some of the other things we found across the course of the job, there were some very soft areas, and we had to develop splices. We were driving predominantly 6 metre lengths, and mainly that was governed by the height underneath the drop hammer underneath that excavator, so we could get that hammer up to a certain height, and that sort of 6 metres is basically how the longest length we could use. So when we needed to go deeper, we were able to splice the piles. So developing a splice is a pretty important thing with piling. And then also we found that whilst you can and will damage the top of a pile upon driving, on cutting that pile to the design RL, we were able to determine that we were able to get to a point where there was no damage in the retained component of the pile. So it's given us a lot of, this initial project gave us a lot of confidence in the use of composite piles in projects, and it's become a staple. So I'd say, we've driven tens of thousands of piles since that initial project, mainly these smaller diameter ones up until now, on boardwalk and pedestrian bridge style projects all around Australia, the US, and the UK. Now, on a small boardwalk, sometimes we look at things and go, why are we driving 6 metre deep piles? So the Pioneer River, Mackay, it is a cyclonic area, and not that long after installation, Cyclone Debbie came through, for those of you that like looking things up. And you can see here the amount of debris over the boardwalk. So when we design these structures, we don't only design for a water flood force, but we're also designing for a debris mat that would cover the handrail and basically increase the sail area of the structure as a horizontal force is applied. So, those piles have been tested and tested to the full force that nature intended there. I'll hand over now to Dr. Ali Mohammed to continue the process of this presentation through our design section. Thanks, Ali.
Thank you, Michael, and thank you, Kelly. Very good introduction from my colleague, Michael. And the question is basically why FRP, or why we need the utilization of FRP. Simply, it can be lightweight and durability, where the traditional material can severely struggle, especially in harsh marine environments. So, for example, we can see here the timber piles are being deteriorated badly, and steel piles are corroded in marine environment. On the other hand, we have very durable FRP piles, as we can see in the photo to the last right of the screen, and which is basically for a project being installed in the Brisbane River, and it survived 2 floods, and it's been in service for 12 years with no signs of deterioration of the FRP whatsoever, except these small dots in the stainless steel hardware for that specific post. But to give a direct comparison on the performance between FRP and other traditional material, the next photo can show a better or a direct comparison. Michael, yep. So basically, this is a photo that I use to show a direct comparison between the durability of FRP and other traditional material. So as we can see here, this is it's not a piles, but it's an FRP. It's a structure with FRP components. So at the back, you have handrail post being installed in this pitch axis structure. It's been installed 10-12 years ago. The 2 posts at the bottom is basically been damaged by vandalism a couple years ago, and the council engaged a local mob to replace the damaged FRP post. The local contractor used carbon steel to replace the two bottom FRP handrail posts, and just after 18 months in service, you can see how they are severely corroded in that harsh marine environment compared to the freshly locked FRP post, which been in service for more than 12 years at the time. So this is the main reason or very good point why FRP can be very durable or can be utilized in such harsh marine environment. But the next question is, what makes Wagners FRP piles very suitable for a driven application? So in the next slide, what we're gonna see the fiber layer of Wagners FRP profiles, and that's basically what makes them unique and what makes them very suitable for driven application. So as we can see here, we have the fiber layer of the 301 CHS profile. So basically we have 17 layers of fibers. All of them are individual rovings. And so we have the fibers that go in the zero direction, which provide the main strength and stiffness. But in between every longitudinal fiber layer, we have a transverse fiber layer, which are also made of individual rovings. And these individual rovings basically provide the transverse strength, but more importantly, they provide the confinement for the longitudinal fibers, which make them basically like it's very stiff compared to the traditional FRP, and basically that enables them to take the impact from the hammer or to drive these FRP piles without exceeding their driving stress. The next slide, it's gonna talk about design consideration or design notes worth considering when it comes to the design of FRP piles. So the two key points that I would like to share here is the skin friction angle between FRP and the soil compared to traditional material. So what we have in this graph and that schematic diagram on the left side. So basically a direct shear test being undertaken on FRP and steel and wood as well, but we're talking here about mainly FRP and the steel. So basically we have this direct shear test is being undertaken on two samples, FRP and steel, by having the FRP and the steel sample and having the soil on top with a perpendicular force to provide that compression force, and also like a shear force to measure the skin friction angle between the soil and the pile material, whether it's FRP or steel. For that specific type of soil sample, 5 soil types being used with different internal friction angle, and as we can see in the graph at the bottom, is basically for the same soil type, the FRP provided higher skin friction angle, and which means basically the shaft adhesion we get from the standard or from the normal geotech reports, it's slightly conservative, I would say by 30% conservative when it comes to the FRP piles. The other component or the other part, which is basically applicable to all hollow piles, which is basically the plug length ratio, which is basically means that when driving the pile into the ground, the soil will go to the inside of the FRP pile and to specific length, and that plugging effect can create basically a plug. But two points worth considering here, based on this study or based on other relevant studies. What can be considered here is basically the internal friction or the internal shaft adhesion, FRP pile, considering the plugging effect from the inside, and that shaft adhesion is basically simplified and can be translated as an additional factor from the outer surface of the FRP pile. Based on this study, basically the parameter or that factor can vary between 1.1 up to 1.5 or 1.7. And the other part of it is basically like this plugging effect can be used is basically to provide that bearing area at the bottom of the pile to provide the end bearing. So to simplify this process on our daily design when it comes to the FRP, as we're gonna see like in the next slide, these two components can be simply translated into basically into the bearing area and the shaft adhesion of that specific pile, considering the outer surface only, without considering the internal friction. And also when it comes to the end bearing, is basically considering the bottom of the pile as a solid surface, considering the plugging effect and ignoring the internal shaft adhesion, and ignoring also the additional skin friction angle we are getting from the FRP as a material itself. And that's basically for the geotechnical design of the FRP pile under axial load. Under lateral load, there are many ways of how to approach the lateral load of FRP piles, depends on the application, but it can be basically like using the well known and the most widely adopted theory, Prohm's theory, or Perch-Hansen as well. But what we generally use to provide more realistic behavior, especially when it comes to deflection, as the FRP piles are mainly governed by the deflection limit under lateral load, especially if the above ground height is substantially high. What we use is basically we use a space gas, or more specialized software can be used as L-pile, and basically we simulate the embedment depth of the pile, and basically using the soil stiffness factor, which is basically an input can be taken from the geotech report, and you simplify it as a cantilever post with the soil stiffness, and that's basically predict the behavior or the lateral behavior of the FRP pile embedded into the ground. When it comes to the design verification or the installation verification of these capacities of these piles, as Michael mentioned in the introduction, the most widely used method is basically Heiley formula, and that's mainly for the axial capacities. And we have developed like a good correlation between the drop hammer weight and height, and also with different type of soil, and mainly with the pile load capacity, and to predict the settlement per plow, and that basically verify the geotechnical pile capacity of the FRP piles. When it comes to the structural capacity of the pile itself, we covered that in the previous webinars, but it can be simply taking out from Wagners CFD design guide, where you have the axial capacity and the moment capacity and the shear capacity of these piles, and we can do like a direct checks based on these values presented in the design guide. So as I mentioned, Heiley formula is one method of verifying the axial pile capacities. Other methods can be done as we can see in the next slide here, where basically like the testing can be done as per the piling code. But this slide is basically show that the next two most popular methods when it comes to piling test. The first one is the static piling load test, as we can see in the photo on the right of the screen, where we have a 301 pile is being statically tested based on the ultimate pile design load and factoring up the geotechnical parameter. So this specific pile has a design load of 100 kilonewton, 110 kilonewton, and considering the geotechnical factor is basically this pile is being loaded up to 15 ton by stacking the loads and on top of the pile and measuring the set during the duration of the test. The other method, which is more accurate and more depends on the project and depends on the project budget, as it can be like a costly exercise. But what we can see here is basically the graph of the PDA test, which is basically predict the pile compressive strength or compressive resistance based on the PDA test, which is basically a drop hammer dropped on top of the pile, and there are several the transducers and accelerometer being attached to the body of the pile, and that's basically being analyzed using the PDA and converting that into the compressive resistance or the axial capacity of the pile itself. When it comes to the driving and the installation of these FRP piles, there are several methods as it's shown in the next slide. So these methods, again, any of these methods can be implemented. It mainly depends on the contractor preference and the contractor capacity in terms of what equipment do they have on site, what's experienced operator do they have on site. The drop hammer, and everyone has its pros and cons. So the drop hammer, the beauty of the drop hammer can be used for driving, and also it can be used to verify the axial capacity of these specific piles when it comes to the testing by checking the pile set per drop. The vibratory hammer also can be used, and the impact hammer, which is basically a rock breaker mounted on excavator, and it's provide several impacts per second and drive the pile into the ground. So this is basically increasingly used now in the FRP pile or in the piling industry overall. And the beauty of it, it's very efficient and it's very quick and minimize the installation time substantially. However, we're still working on a correlation on how can we use this impact hammer for driving and also for verifying the axial capacity. So we have done several trials, which is still work in progress. We are working closely with the University of Southern Queensland and with several local engineers that we generally use for the certification of our structures. So basically, we have driven several piles into known strata by having a proper geotech on that specific area, driving the pile using a drop hammer and the impact hammer, and measuring the strain and the pile set while driving. And as we can see in these two graphs, the first finding and the most interesting finding that we have so far is basically in the top graph we have the strain gauges and the strain readings from these FRP piles, and as you can see, it's basically the strain goes all the way up and down back to 100 microstrain and 200 microstrain, but it goes back to zero after or reset basically between each drop. However, in the impact hammer, basically the strain built into the pile and the next drop came into the effect while taking the strain to the next level, and that basically provide better driving performance and more efficient and quicker way to install these FRP piles into the ground. But we are still working on trying to verify and having a way to determine the axial geotechnical pile capacity from the impact hammer by itself. Now I will hand over back to you, Michael, and to finish these slides, and we'll take all the questions at the end of this webinar. Thank you.
Thanks, Ali. So that's given us a really good overview of, I guess, some of the design work that we've done, and I guess, gives us the confidence to say that we've got a solution for piling. It definitely works as a pile, but again, there's many different environments and different styles of pile that are needed, particularly in these marine environments. We've developed a coating, so we've got a HDPE coating on the outside of the piles. So the same pile, the same fiberglass profile, but this time with a HDPE sleeve integrally connected to the outside. So what we have seen is that in particularly these marina type applications where you have floating structures connected to the piles, so generally they're connected by a frame with small wheels or bumpers, I guess, that as the tide comes in and out and they float up and down on the pile, they rub or wear or braid onto the pile itself. So basically the HDPE coating in these instances is designed for these type of environments where you have a constant abrasion or a constant impact on the pile. So we see those being used particularly in residential marina type applications, or in areas of high debris loading where, I guess, additional armouring on the pile would be warranted. Go to the next slide. Other things we've had to develop over time: driving hardware. So helmets, we've developed driving helmets to, I guess, sit on top of the piles and connect to the various driving techniques that are out there. Generally, we're trying to match someone else's driving unit, and the question is, well, how do I connect from my driving unit to your pile? So we're very keen to, I guess, work with companies to develop and supply, whether it's a helmet or some other technique, work through the issues. And of course, splices. So here, on the left-hand side here, you can see a number of splices we've employed. We've done external. We're currently developing internal splices. And it's, at the moment, most of our splices are bolted, so a fairly simple arrangement to be used in the field. We're not looking at bonding or anything like that in the field. So we're trying to keep it to a simple connection. So that's all development, well, constantly under development. Whilst we have solutions today, it's things that we're looking to improve. And also, I guess coming soon, larger diameters. So today, that most of the early work that we did with our pedestrian structures, 100 by 100 or 125 by 125 millimeter square profiles. Most of the work Ali is working on there at the moment is using our larger circular 300 diameter and 356 millimeter diameter profiles. To go bigger than that, pultrusion is a fantastic process with volume and lots of volume. So that the 300 and 356 we're using as power poles and piles, so it doubles up. It's got quite a large demand for it. For smaller quantities, I'm talking hundreds of, as opposed to thousands of, filament winding is the preferred method. So we are putting in a filament winder at CFT to produce power poles and piles. The length of the products we'll produce will be 15 metres maximum length, or less, but up to 15 metres, and up to an 800 millimetre diameter. So we'll be able to produce some large profiles where we've got the machine designed, as you can see, to have a fairly flat wind angle. So that this simulation is a filament winding software that sort of depicts the fibre layup on the pole. With pultrusion, we have 0 degree fibres, so fibres that would run straight up and down the pole. Can't do that with filament winding, or not very easily, but we can get as close as we can. So here you can see about a 10 degree wind angle going onto a pole, and we'll get something like 80 to 90% of the properties of a 0 degree fibre. So early next year, these will be available, and we're ready to start talking about supply today. And from a procurement and supply site point of view, the 300 and 350 millimeter profiles, we can make about 50 piles a day, piles/piles a day. So it's something that it's not necessarily a quantity constrained item. It's something we can produce fairly quickly, roughly 1 an hour. And on the right-hand side there, you can see us loading these sections onto trucks. So we're typically packing them in a 7x7 arrangement. So it's 49, they're 12-meter lengths on those trailers. So 49 lengths on a trailer, and in a B-double configuration. So we've got 98 poles or piles heading to a customer with every B-double. So it's good value compared to sort of one concrete pile or a few steel piles on a truck at a time. So we see that there's a lot of sort of savings in other areas, and mainly that's in the transport and in the handling. So the very light composite piles, we're not needing massive equipment to install them. That's one of the key benefits that we see. From a installation point of view, what we are setting up to do here at Wagners is we'll quote a project. So for years, we've been quoting boardwalk and pedestrian bridge type projects where we will specify or design in composite piles. We have bought one of these drop hammers that you see on the screen dropping away. Now, it can be used on from a 7-ton excavator to a 14-ton excavator. It's got a grab on the bottom for picking piles up. To use it in the configuration I've got on the screen at the moment, you'd want the 14-ton excavator. I'll just play it again. If you have a lighter excavator and you don't need the grab, we can take off the grab and use it with a 7-tonner. So that's got a bit of flexibility in how it can be used. We have a impact hammer. I think Ali referred to it as one of those vibrating. It's like a rock breaker, but instead of with the point for breaking rocks, it's got a plate on it. Now, those plates are machined from a single billet, so they, as you can imagine, they cop a fair bit of abuse with the vibration of the unit and pushing down on the pile. So it's quite a specialist bit of equipment. So with the Thor hammer, so with those you'd require a 14-ton excavator. And of course, with most of our projects, we always have that offer to send a technician to site to help a contractor for a few days, a few weeks to get going, whether it's the manufacture of the boardwalk or the driving of the piles. So we're keen to be involved in projects, and at the end of the day, we want to see them done well. It's people are often buying composite products so that they get a long life asset, and we are very motivated to ensure that is achieved. So Kelly, I'll hand back to you. That concludes the technical content of the presentation, and happy to open it up.
So I'm just going to jump in now quickly. Thank you very much, Michael and Ali, for your presentation. We're about to dive into the Q&A session now. So if you do have any questions, pop those in the chat box. But just before we do, I want to tell everyone very quickly about where you can find some more information on piling, and also how Wagners CFT recently integrated its FRP library into engineering software application, SpaceGas. So for more detailed information on the process of piling, check out pages 8 through 11 in the Wagners CFT installation guide. These pages provide comprehensive guidance on the best practices necessary to optimize your pile driving techniques. Whether you're looking for step-by-step instructions or technical specifications, this section of the guide is designed to ensure a thorough understanding of the piling procedure. These pages will provide you with valuable insights that will help in optimizing installation and ensuring structural integrity throughout the process. So if you'd like some more information on piling, use the QR code on the screen there, or I will also send the link in the follow-up email after today's webinar. Have you ever needed to manually create an FRP section in space gas? If so, you would understand how incredibly slow this makes the whole modelling process. Thankfully, this is no longer an issue with the integration of the Wagners FRP library into space gas. The new Wagners FRP library allows engineers to quickly and efficiently incorporate FRP members into their design without the hassle of manual creation. This new library addition reduces time and costs associated with the design and analysis of projects. And the best part? Everyone who has space gas gets the library as a standard library from version 14.25 and beyond. The library is even included in the free student edition of space gas. To read more on the integration of the Wagners FRP library into the space gas, scan the QR code on the screen now, and this will also be provided through the end of webinar email. Okay, I'd now like to introduce Wagners CFT General Manager Ryan Leeson, who will be facilitating the Q&A session of the webinar today. Let's have a look at some of those questions, Ryan.
Thanks, Georgia. Good morning, everybody. Kempi, first one for you. Looks like this is from probably a marine contractor, I'd imagine. The hammer weight of 750 kilos is very light compared to typical hammers on a typical rig. And also a comment there that the drop height of 500 mils is also quite small. Is there a spigot available to allow it to be used on a 2-ton drop hammer with a 2-metre drop? Which the comment is there, that would be more typical and obviously a more heavier application, I'd imagine. I think you're muted there, Kempi.
Thank you. Look, it's horses for courses, and depends on the application you're in. So to date, most of our structures are pedestrian structures. We haven't done massive high loading structures, but we can see that there is demand for composite materials, and we're heading that way. Part of the reason for the webinar is to communicate what we're doing, and to encourage other people to contact us with opportunities and challenges such as this. So with higher loadings and higher impacts, we have to be mindful of the impact applied to the top of the pile and how much damage we're doing to it, the energy at the bottom of the pile, what it's going into, and make sure we're not destroying the pile at the top or the bottom. So I guess it's balancing that with the need to drive through. I've seen projects, a particular project at Harvey Bay I can remember, where a minimum embedment was required and a steel pile was hit over 400 times to achieve a minimum embedment. And my question was, did you achieve a minimum embedment, or did you smash the rock at the bottom? So I think it's coming, and I agree that they're light compared to sort of larger applications, but at the moment that this is the trajectory that we're heading towards.
Thank you very much, Kempi. Maybe also for you, how does the cost effectiveness of FRP piles compare to conventional concrete piles or other typical types? I can support you on that one if you need.
Yeah, I think typically, if we're talking generally, Ryan, if a timber pile will do, it will be less expensive than a composite pile. There's no doubt about that. The composite piles are more expensive out of the gate. And that's why, particularly in this webinar, we focus on things like the freight and other things to consider. Often what we see is that fiberglass profiles of any arrangement are not far off a galvanized steel cost by the time you've got that. When you're looking at installation, if you can use the lightweight, for a boardwalk with a narrow corridor where you have to traverse all of your materials along the length of that corridor, I wouldn't use anything but composite because of that weight and the ability to move things up and down. So where you use the lightweight or the non-corrosive nature of the material, it's a no-brainer, and it's cost neutral, at installation, and offers a better whole of life cost. But where it is more expensive, it's going to be up on its merits.
Very good. Ali, maybe for you, do you have a BIM package or Revit families available that sort of accompany the space gas library? I'm guessing that's a question on the back of.
Yeah, we have these BIM basically families are available, and that's what we use basically in modeling and drafting every single one of our projects, and we have shared that with many consultants and anyone who would like to use them. And if you can, or maybe we can include that in the follow-up email that after this webinar as well.
Okay, Kempi, what is your experience with pile driving performance and damage when encountering floaters and or rock? Any exhumed inspection evidence to date? And I guess more broadly, the material types that composite piles are typically suitable for?
So I've missed the second part, Ryan.
Just more broadly, material types that composite piles are suitable for. What sort of material stratas have we driven them into?
So, most of what we've done to date has been either sandy conditions. So it's been boardwalks and pedestrian bridges. So we're either on the coastline, close to the coast, or for example, in Mackay, we're in the floodplain of the river. So we're typically talking, clays, sands, alluvial deposit sort of thing. We're not, driving through rock. What we do tend to do is look at, before you go to a site, you look at like a simple tests, DCPs, direct cone penetrometers, so we can correlate sort of DCPs to the ability to drive composite piles. It gives a good indication. These types of examples. So that's traditionally where we've done it. As I said earlier, if you've got a hard rock strata and you're trying to drive through it, or to get a minimum embedment, and you've got a serious impact loading on the toe of the pile, we're not there today. To the first part of that question, we have driven piles and pulled them out. For any application where we get, we sort of do get a reflection of the damage on the top to the bottom. It's the same energy going into the top as being imparted to the bottom. So if we're seeing no movement and we're flogging the top of the pile, that's where we're pulling up generally. On removal of piles, we've seen no damage, apart from when we know, we've actually tried to go further than we knew we should, and then we have seen damage on the bottom. So it is fairly intrinsic. It's a visible thing, and it's a manageable thing.
Okay, how do you cater, Ali? How do you cater for installation requiring uplift capacity? Is it exactly the same as your skin friction in reverse? Just muted there, Ali.
Yep, it's exactly like that, Ryan. It's basically the shaft adhesion in reverse, and plus the additional dead weight of the structure, which is not much in case of FRP structure because they are lightweight.
Okay, and maybe to follow on from that, when bolting joints or attachments, what is the typical design bearing stress?
Yep, that's another good question. And we usually have all the bolted connection capacities are presented in tabular formats in the design guide. So rather than relying on the bearing stress, which provide additional step when it comes to the design by converting that bearing stress on the bearing area to get your force. So we have all the bolted connection capacities are presented in the design guide for M16, M20, M24 with inserts, with steel tubes as bush inserts. So all of that is basically presented in the design guide.
Very good. Kempi, UV degradation, same applications as the rest of our structures, I'd imagine.
Yeah, that's right. So UV degradation of the resin is, I guess, the one thing that can affect composites. And across the board, we coat all of our composites, particularly for Australian use. We've found that UV in Australia to be far in excess of, or the damaging effect of UV here in Australia, far in excess of anything in the US or certainly in the UK. We paint everything. We use a fluoropolymer paint system. I think we've done other webinars on that coating system as well. So I'm sure Kelly will point you towards where our other webinars are, which will go into some detail on that. But yeah, everything we do has that coating on it.
you maybe want to talk, Kempy, to the cross arms, the original cross arms that we pulled down, and how the structural strength of those actually improved, because after 20 years or whatever it was?
So the cure rate of resin is similar to concrete, where you'll get we'll get an initial increase in strength as it goes from a liquid to a solid. We're getting to that curve, and then that strength gain curve will flatten off, but it's not flat. It actually continues to grow, just similar to a concrete curve would. So I think just about in every case where we've taken for example, a pile or a piece of a structure, replaced it with a new one, obviously, brought it back to the lab and done some testing on it, we've seen generally a higher modulus or a higher flexural capacity because of that continual sort of strength gain with time. So it's from a UV point of view, the issue will be that you get fibre blooming, and that's what we don't want, and that's what the paint covers.
Okay, keep going on a couple more questions here. Ali, while the driving method correlation that you spoke about is unfinished, the method that contractors have been doing to date is just using either a vibe or an impact hammer and then switching across to the drop hammer for the validation testing. Is that correct? And that enables the use of the formulas that we spoke through. What we're trying to do is avoid that need for the changeover in piling methods to enable that validation. So then the impact hammer can be used to get that correlation at the time of driving. That's just to broadly summarize, that's what we're working towards?
Yep, that's a good summary of it, Ryan. So basically, like for a boardwalk that has 400, 500 piles, rather than driving all of them like an impact hammer and take months. So what we can do, or what's been currently done, is basically driving all of them using the Thor hammer or the impact hammer, and to do to have all the whole pile driving process in few weeks, and do the interchange to test 5%, 2%, 10% of these piles in the drop hammer and verify that basically the geotechnical axial pile capacity using Hiley formula.
Okay, and Michael, the fibre layout that Ali sort of went through, how is that specific to Wagners? And does it mean that profiles that use glass mat rather than direct rovings, the damage would propagate further through the pile? So in composite piles, I believe the top little bit's cut off just with a saw after the driving, but the concern around propagation from any piles that use mat that's where the real concern comes in.
Yeah, I think so. If you look at our pultrusion that we've developed here in Australia, it's that circ wound pultrusion. So you see lots of different angles of glass. Now, pultrusion generally is all longitudinal fibre, and so 90% longitudinal fibre and a very small amount off axis. If you try to drive one of those pieces of pultrusion, you'll find that the energy that you can impart to the top of the pile, i.e. your hammer mass and drop height, is a lot less before you start doing damage. So you literally start, failing the top of the pultrusion. It'll crumple, or it'll bend up the longitudinal fibres. In the Wagners profile, you've got lots of wound fibre around them that confines, and Ali spoke to confinement, confines those vertical fibres so that they are acting to resist that impact load. So we've seen that, general pultruded profiles will not react the same way as Wagners pultruded profiles. They are high modulus and with a high degree of wound fibre to confine those longitudinal rovings. So again, they're very, very different grades of composite.
Just again for you, Kempy, at the start, there was a discussion on the height or the length of the piles being constrained to the piling equipment that's being used. And again, to the earlier question that was made, in these applications, often the equipment or the plant being used is 5 tonners, 7 tonners, that sort of range equipment. So the stroke length isn't very much. Is there, just maybe want to go through some of the tips and tricks others have done with pre-augering or side gripper driving hammers? Is that something that you've come across?
Yeah, so often I think is the questions about pre-drilling holes. So yes, we've pre-drilled, and there's obviously no issues with pre-drilling. Often, if you want a longer length, if we want to drive to 6 meters, preferably you're not driving 4 meters and splicing because you've got a small excavator. So we'll pre-drill a hole and get the 6 meter length in the 2 meter hole, and then your 4 meter height of your drop hammock and drive it in. So that's a technique. In Papua New Guinea currently, we are pre-augering into an alluvial sand across an inlet, an ocean inlet, and then driving into it. So I guess we're clearing the way of, I think there was concerns about floaters in the comments. So we're clearing the way. We're making sure we've got a clear run and then driving the 300 diameter profile in. That same project, we have got a side gripper vibrating driving head. So the grabs actually pick the pile up, and they're mounted on the side of the vibrating unit, and the excavator operator keeps that pile straight as he's pushing it in, and the unit's vibrating. So that's probably another style that we haven't used a lot of. It's the first project using the side gripper, but it's another style of driving, and we're having success with it.
I think that might also answer that last question there on suitable to be driven into pre-drilled holes, Ali, but I'm not sure if you want to just cover on that quickly. I mean, yes, if there's different strata layers, you can pre-auger through them and then enable the embedment that you need below that layer. I think maybe a lake or boardwalk or something on the Gold Coast, we did a bit of that as well. Ali, do you just want to comment on that one as the last question?
Yep. So it's in addition to what Michael mentioned about the practicality of having these extra long piles, and by pre-augering or pre-drilling basically a hole into the ground. The other scenario is basically where we have a rock at 4 meter deep, but the whole soil, like from like for the first 4 meters, is very bad, geotechnically bad soil. So what generally can be done is basically augering into that rock and dropping the pile, and usually like backfill it like with a specific type of grout or concrete, and that's or basically like backfilling it like with the specific type of soil, whatever suitable based on the geotechnical conditions and depends on the design. But basically, yes, we have done that. Is basically by pre-augering into the rock to achieve that higher geotechnical capacity, and placing the pile into that pre-drilled hole into the rock layer.
Thank you, Ali. So I guess that closes out the questions, and we're running out of time rapidly. So I'll hand back over to Kelly, but maybe Kelly, you can also confirm we're getting a lot of footage and videos and things done on that Papua New Guinean project at the moment. So hopefully that's a video and some more learnings and information we can share with this group in the not too distant future. Thanks everyone for joining us.
Absolutely. That concludes our presentation today. Big thank you to Ali and Michael for their involvement and the effort that they've gone to put that presentation today. And thank you to Ryan for facilitating our Q&A session. I see a couple of questions that have popped in there. We will follow those up. So stand by, Trevor. I'll give you a call later on. Before you go, if you would like to share your thoughts on today's webinar, please feel free to complete the feedback form. That would give you an opportunity to ask any more questions that you would like us to follow up with as well. If you can't access that QR reader there, I've just popped the link into the chat there for you, and we will also include that in the follow-up email that will be coming out later today. If you'd like to be a guest speaker, that form is also perfect for you to fill out and complete and send back to me. Reach out to me on LinkedIn, send me an email, however you want to contact me. We'd love to hear from you. Coming up in May, we'll be exploring the design, construction and performance of FRP raised nest platforms and the impact they're having on South Australian osprey numbers, with Ian Falkenberg from Friends of Osprey, Kevin Betterman from the Androssan Community and Men's Shed, Rick Hawthorne from Southern York Peninsula Landcare Group, and Janet Moore from Northern and York Landscape Board. So if you're interested in attending that webinar, just use the QR code on the screen now to register for your free online seat or to receive a recorded copy of the webinar. again, we'll add it to the follow-up email, and I've just popped that link into the chat there for you too. That concludes our webinar today. Thanks very much for coming. We're going to go out on that fantastic piling video that we saw coming in, and we look forward to seeing you in May for the next webinar on the osprey nests. See you then.